David is not here, but
I think he's going to come. He said he was going to come. For
yeah, no, but
we have to at least wait.
you can ask
So if
questions from Daniel's class.
If you don't ask me questions, I will give you exercises to do. So start thinking.
Oh, you had a graph towards the end, right? Which was the it was probably A over delta versus alpha. Or
Yes,
something.
so this I stole from David, right? So what do you want to know about it? So if I remember correctly, and maybe you can ask him when he comes back, right? So the idea here is that I have a square well potential. Which is, I think it's alpha over delta squared. Like this.
3 over 4 pi r cubed.
There's a 3 over 4 pi. Okay, thank you. And then I solve this and I ask what happens to the scattering length. Sorry, this should be delta. What happens? And so then the scattering length here, and this is attractive potential. So I'll put a minus sign here. So as I make the potential more attractive, so I start off with a small negative scattering length. And then, but the scattering length is non-linear in the coupling. And so then at this point where, what is it like where the strength actually is the overall strength is related to the range by some factors of pi over 2, right? Then I get this, then I get my first bound state appearing.
Oh, but maybe, no, then it was probably another one.
Okay. What, another graph? Okay.
Which started from the origin, went up and came down.
Oh, it was the wave function? Yeah. Okay. So let's talk about the reduced radial wave function. So here I have my normalization factor times my bound state. Sorry, let's do it this way. So this is this thing. So it's related to the full wave function by a factor of r and a factor of root 4 pi. Good. And then I said, okay, so suppose we like to work in coordinate space. So we make some local potential in here. I don't actually care what it is really. But the point is that whatever this local potential does for me, it has to reproduce the logarithmic derivative at this point. So basically the role of this potential is solely to get me the right log derivative at the boundary. And then as I take this range into 0, that continues to be true, but I quickly see that in the limit that this potential acts only at the origin, I will have the right log derivative, but I'll have, if you like, a wrong boundary condition for the u itself.
Yes, but this was for the attractive case, right? For the repulsive case, it's not supposed to start at the origin.
For the repulsive, I mean, you always has to start at the origin. But for the repulsive case, it's going to be some hyperbolic sign instead of some.
Doesn't this negative, I mean, the slope, minus of the slope is supposed to be the scattering length, right?
Ah, that's another graph.
Oh.
If I plot the phase shift versus momentum, then, okay, so I've got to figure out how far back I want to go. Okay, so we have, let's start with this, okay? So now let's go to k equals 0. So as k goes to 0, this goes away. Cotangent delta for small delta, the small delta behaves like 1 over delta. So for small delta, at very low K, delta of K will go like minus Ka. So for an attractive potential, A is negative. Okay, so for an attractive potential, the phase shift looks like this at low energies. So that's what you were asking about, yes. Okay, and then the problem with this is here I approximated the cotangent by assuming that the angle was small. So then at some point this fails and this sort of saturates and then the phase shift turns over, although this happens all. And this is kind of related to Abhishek's question from this morning. So this scale here is actually over which this turnover happens is 1 over A. So if K times A is much less than 1, you could take this to be linear. But if you're interested in the regime where Ka is of order 1, then you can't do the Taylor series in assuming the phase shift is small. If the phase shift is, if the potential is repulsive, then this goes down from 0. But you also have the situation, which we'll talk about more tomorrow, where you can have a positive scattering length and a bound state, in which case the phase shift goes down from 0, but it changes by pi between 0 and infinity. So this is, in fact, you can show that if there are n bound state, it changes by n times pi. So this is attractive, no bound state. And really, and then the other graph, which I haven't drawn, would be something like this, where this is repulsive. So these are sort of like the 3 cases that you want to think about when you're thinking about what phase shifts do at low energy.
Thanks. Thank you.
Yes. Yeah, for those of you who've heard of it, this theorem that delta of 0 minus delta of infinity is equal to n times pi, where n is the number of bound states, is though this is a little bit tricky in EFT, because in EFT you only really have access to the phase shift over a finite. So this actually tells you that the EFT can have like deep bound states or things, and you actually don't care because you could integrate those out. But if you have those deep bound states, then Levinson's theorem will actually give you a different answer to what you want, right? So, yeah. Yes.
Nuclear EFTs have this rotational symmetry and the parity symmetry, or
I'm going to sit down to think about that. No. Okay, so let's start with parity because that's easier. So if you wanted to write down an effective field theory for hadronic parity violation, so like you were interested in parity non-conserving potentials between nucleons. So those are going to exist, right? Because inside nucleons, I drew just quarks, but inside nucleons, I could also have like some, how do we do this? Some W boson exchange or something, right? And then this could generate some parity violating, and then maybe this cup, maybe we get some, and then somewhere in here, this spits off a pion. So this will generate some parity violating pi NN coupling. So if you want to study this, you have to write down operators that violate parity, but you should also, the one thing you're going to have to decide is if you're interested in parity violating time reversal conserving operators, in which case you have to make sure that you break the symmetry in the same way you're interested in. Yes. So these effects are weak at low energy, right? But you could write down, but you could do, so I have actually worked on this a little bit, right? So you could do it, essentially all the operators are suppressed by GF, but then you could expand the operators in powers of momentum, right? So then you have they're all small, but some are smaller than others because they're suppressed by powers of like momentum over some high scale in the EFT. Okay, so rotations are, so the pion, okay, so let me think about this for a minute. Yes, so you have rotational symmetry because the symmetry group is in general going to be the Galilei group, so like small boosts and rotations, but you don't always conserve angular momentum. Because you can have because you conserve J, but you don't conserve L and, right. So for instance, the most famous example is that at least for me, the most famous is that the deuteron is not a pure S-wave bound state, but it has some admixture of D waves if you treat it with pions. This has actually historically been a sort of an interesting point of discussion about these short-range EFTs that are dominantly S-wave. Like, so, okay, so then how do you deal with the fact that the deuteron has a quadrupole moment? And there are answers, but in that, so it turns out that in those formulations, you have to include, so maybe the answer to your question is no, I'm not quite sure. You have to include operators that mix S and D waves as higher order effects. But they still are overall rotationally symmetric. Right, but because they're like, you know. Right, we can do P, whatever, I don't care. That's P hat, so yeah, something like this, right? So you're going to have some tensor in S coupled to some tensor in P such that the overall thing is rotationally symmetric. Sure. So sure, I mean, if I compute neutrino nuclear scattering, then all the operators have a GF in them, sure, yes. Yeah. Yep, there are a bunch of calculations of neutrino nucleus, ranging from like the deuteron all the way up to, you know, 016 and beyond, so yeah. So it's been done in these short-range EFT for the deuteron. I'm not sure it's been done for anything else. But yeah, but I can give you references if you're interested for the deuteron, right? But then, yeah, but like in some sense, how do I say this? That one is a little bit easier because you have some external probe that interacts once with the nucleus and its coupling just factors out of the overall amplitude, right? So there's just like an overall GF in the amplitude, right? So yeah. And in some sense, the neutrino nucleon couplings are given to you, right? Here, this one is a little bit more interesting because there's non-perturbative dynamics going on here. You know there's an overall GF, but then you don't know what the rest of the strong interaction coefficient is, right? So yeah. Yep.
Is it based on the observation that neutron has small EDM?
But that would be time reversal violation, right? The EDM is time reversal. Yeah, so that would be time, right? CP or right? Because I believe in CPT, right? So this one is. So how would I say this? This is. So this has been experimentally measured. So what this means is that you get like. So this is kind of fun, right, in the sense that you get transitions like this. You can get transitions between different partial waves that shouldn't mix if parity was a good symmetry. And so you can measure this by looking at asymmetries in like neutron-proton scattering. There was a lot of activity about this in the 80s, and these asymmetries are not zero. And so from this, you can pull out some information on the size of the hadronic parity violation. And it's, you know, and then there are other things you can do by looking at certain transitions in nuclei, which again would be zero if parity was a perfect symmetry. So, yeah. But they're all like, I don't know, order 10 to the minus 7, something like that, right? So they're all, right, because it's like G Fermi times the momentum squared. Yep. Yes. Yep. So this, maybe you should ask me this question again after tomorrow's lecture. After tomorrow. So, but because tomorrow I'm actually going to show how you do the next to leading order correction. And we're going to see, you know, that it comes in through this operator C2, and, you know, it's suppressed by the size of C2 relative to C0, which I think David said in his lecture is, you know, R times A, and so on and so forth, right? So, yeah, so I think this is probably an easier question to answer after we've seen a concrete calculation, because I think there are two parts to your question. So the first part is, so as you said, and I will talk about this tomorrow, when you go to next leading order, you still don't have the effect of what we call the shape parameter, or the fourth order term in the effective range expansion, right? This only enters at N3 LO. This I will be able to explain tomorrow. And the second part of your question is, if I did this, like, at what order do I get SD mixing? So yeah, but to do this one, I will be able to explain tomorrow. This one I will need to think about, and probably, I think I can explain this once Professor Kaplan has introduced his PDS scheme. Right? This requires you to have accounting for interactions in different partial waves. So yeah. I will say a key point in these EFTs is that S waves are special because and I'll talk more about this maybe tomorrow, maybe on Wednesday, right? So S waves are special because in S waves you can have these shallow bound states, and you can take, at leading order, you can take the limit that the range goes to 0. So one way to say it would be that you can achieve the unitarity limit in physical systems in S waves. And so that means that in these systems, the S wave amplitude gets enhanced, but typically you don't have enhanced. If you have this shallow S wave bound state, you're not going to, for low energies, your P wave scattering will still be natural, and so will your D wave interactions. And so this means that these other partial waves that tend to get significantly suppressed, because not only are they suppressed by the fact that you need more powers of momentum to generate that higher angular momentum stuff, but they're also suppressed just because they don't have a low energy enhancement. So yeah, but I can say more about this tomorrow. All right. Yeah, let's do, okay, so what time officially does the Q&A start? 5? Does someone have the schedule pulled up? 5, okay. So that means we have about 15 minutes. So let me find something here. All right, so I'll give people, okay. So the first thing, how many of you are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so let's make 8 groups of 4. So the 4 of you can be a group, and the 4 of you can be a group, and then, you know, find 3 friends, or if you don't have 3 friends, make 3 friends, or make 4 minus n friends, where n is the number of friends you have, unless n is larger than 4, because that would mean giving up friends. Whatever, you get the idea, right? So, and you can choose to solve one of the following 2 problems. Or if you're quick, you can solve both. All right, so the first thing is to show, basically do the integral over P0 that David and I kept doing and that you might have wondered how we were doing, right? So show that in the one loop diagram in a non-relativistic EFT with a contact interaction. And these are meant to be like, you're meant to help each other. The P0 integral can be done. And it yields the non-relativistic Green's function. Okay, and to make this fun, let's do 2 different fields, like I was saying about. We'll have a boson field whose mass is mc, and a fermion field whose mass is mn. And then I want you to do, all right, the integral in this loop, the P0 integral. But I want you to, so you can't sit over there, you have to go over there and find people. Okay, all right, so that's one thing you can do. All right, and the other thing you can do, I've got to find my notes to make sure I get the factor right. This one might require you to look up formulas involving gamma functions. Or I guess you can ask Mathematica, right? But yes, so, and a word of clarification here, because Professor Roy asked me about this, so, and obviously I wasn't clear. So when you're doing this integral, I think for both Professor Kaplan and myself, this integral is over little d dimensions, and little d is big D plus 1. So little d is the number of space-time dimensions, okay? And big D is the number of space dimensions. Okay, so this, if you've been puzzled as to why little d's kept becoming big D's and stuff like that, that's what's been going on with that. Okay, so the point here is that to do this integral, there are 2 stages. The first stage eliminates the P0 integral and takes you from 2 propagators to 1 propagator. And then the second stage, you do the 3-dimensional integral, if this is the one we're actually interested in here, by using like standard like dimensional regularization tricks. Okay. So then a couple of questions you could ask yourself is, so here you could ask yourself what happens if the potential is not a contact interaction, but is time independent? And that's why you need a group, because even if you can do the calculation, you need to discuss this question. And here you could ask the question, how do I analytically continue to positive energy? Because this gamma, remember, was the square root of minus ME for E less than 0. So gamma is a real number, but if E is greater than 0. Okay. You could also ask yourself, for what values of D is this actually true? Okay, all right, go for it.